Hello all and welcome back to another video. Today we are going to be discussing about one of the most fundamental machine learning algorithms and the most basic ones, which is called as the linear regression. The linear regression is actually a very foundational statistical idea which was then used in as a machine learning technique to model the relationship between a dependent variable, which is a target, and one or more independent variables, which are called as the features. So, as the name suggests, linear means we try to fit a straight line to the data so that it can predict outcomes and help us understand how different variables are related to each other. So, as you all know from straight lines, we know that the equation for a straight line is y equal to mx plus c, where if y is the predicted value, m is the slope, and x is the input feature, along with some sort of bias or the intercept, which we call as c. So, here I've just tried to do a sample regression analysis. So the example taken here is that we have two arrays x and y. X is the number of hours that you study and y is the test scores. So if you study for 1 hour, like this is for different students, right? So let's say student 1 has studied for 1 hour and he has scored 2 marks. Student 2 has studied for 2 hours and he scored 4 marks, so on and so forth. So we have the scikit-learn library from which we can directly import the linear regression algorithm. And we defined the target variable and the input variable into two separate arrays and call the fit function on it. So the fit function basically tries to fit all these data points into a line using the linear regression algorithm. And then now let's say we want to predict what will happen if, let's say, another student studies for 6 hours. What is the probable score that he could, what is the score that he could get based on the fact that there are students of who have studied for these many hours and scored these many marks, right? So that is the question that this is trying to solve. And we can see that it is given as 5.8. So this is how linear regression works. Basically, when we are given different data points, we try to fit a line that sort of minimizes the squared distance between the line and the point. So this particular line is unique such that the sum of the squared distance from the line to the point is minimum, and that is the best fit, or the and it indicates the linear regression line. And you can just go to x equal to 6. It's not given here, but at x equal to 6 it will reach 5.8, and so that is how we get the answer or the predicted score, which is 5.8. So this is about linear regression. Also, linear regression has a lot of use cases. One of the main, things about linear regression is that it's very easy to use and easy to understand, especially for beginners. It is useful to, give some basic insights and findings. It is very fast and it is not that advanced. Anybody can implement it. Some areas where linear regression is used, of course, there are other complex methods of regression like logistic regression and so on. But where linear regression used is if we want to predict the sales, house prices, or estimate the demand based on price changes. Maybe we want to model the temperature changes or the pollution levels. So something like that. So one common example that I always see is we want to predict the house price based on the area of the house. So let's say an 800 square feet house is around 80 lakhs and so on. We have a few more data points, and now we want to predict how much 1,500 square feet house would cost. In such a case, we can just apply linear regression along with the historical sales data, and we can estimate the price of the new house, which helps the buyers and sellers to make informed decisions. So, this was about linear regression. Thanks for watching. Hello, guys. Welcome back to another video. In this video, we're going to be discussing about a better method of regression called as logistic regression. Again, this, as the name suggests, uh, you might think that regression means you might be fitting another complex line, but no, this is not uh, an algorithm where we try to fit a complex line or anything. In fact, this is actually a statistical method that is used for binary classification problems, where the outcome is either either one or either two. As in, like it can either be yes or a no, or something like a spam or a not spam email, something like that. The main goal of this algorithm is to predict the probability of the input belonging to either class 0 or class 1. So we'll have two classes, and then it'll be able to predict whether it's more towards class 0 or more towards class 1. And the input belongs to a particular class using the sigmoid function. So using this sigmoid function formula, we are able to obtain the property. Sorry, it models the probability that belongs to an input to a particular class using the logistic function or the sigmoid function. So this outputs values between 0 and 1, and that is how it happens. So in logistic regression, just as we discussed, it is trained to, give a probability number between 0 and 1. And the model is trained such that we need to minimize the difference between the predicted probabilities and the actual class labels. And this is done using a loss function called as the log loss or binary cross entropy. So these are some advanced concepts, but in short, what it means is that whenever we make an error, we get some loss, right? And at the end of the day, the goal is to minimize this loss. So just think of it in that way. So we train our model in such a way that, the sigmoid function, the shape of the sigmoid function um, is represents the least possible loss or the log loss. That is what logistic regression is trying to do. So some, problem statements that logistic regression can solve is email spam detection. It can classify whether emails are spam or not spam. Can do disease diagnosis, whether a person has diabetes or not. So you get the idea, right? A lot of yes or no questions can be solved using this algorithm. Now let's move on to a sample problem or illustration. So here I've just imported the necessary libraries as well as the iris dataset. I have loaded it, and I have just given the target variable. I've just converted as int, and then I've tried to split this data set into the train and the test data set. Why do we do this? Because always when we have a data set, we want to first train and then test it based on some authentic value. And that is the test data set. So usually we just, split the whole data set into train and test. Um, Generally on the 80-20 ratio. Right? And now we call the logistic regression method and we just try to train the model on it using the training data set. Now we just want to, after that, we just want to predict it, right? So all the x underscore test values need to be predicted. And each of them is given a value between 0 and 1, so on and so forth. And then, you can look at the accuracy and classification report. So here we can see that the accuracy is 1, which means that the model that we trained is a very basic model, right? So obviously it will do really well. So the model that we trained here was able to correctly classify um, the class of every data point um, with 100% accuracy, which is nothing but 1, right? And the precision, recall, F1 score, and support, these are all some more advanced metrics to check whether our model is actually doing well or not. So sometimes the model only predicts one particular class and does not predict the other particular class, right? But in such cases, also, maybe the accuracy is going to be high. But then, if it's not predicting an important class, let's say you have credit fraud detection, right? The importance of detecting fraud is very, very high. But then, what if our model is unable to do that? Let's say out of 1,000 transactions, maybe 10 transactions might be frauds, but it is essential to sort of identify these, right? But if our model is able to correctly classify all the, you know, authentic transactions and fails at the fraud transactions, since the fraud transactions is a very small number, the accuracy won't see a big change. But then metrics like precision, recall, F1 score will allow us to see that something is wrong and our model is not predicting things properly. And this is the main reason for having these metrics. This was a brief about logistic regression. Also, let me show you how the sigmoid function looks. Yes. So this is the sigmoid function, and the logistic regression function tries to give an output between 0 and 1, right? Between these two. And based on that, we are able to classify. So that's all for this video. Thanks for watching. Hello guys, welcome back to another video. Today we are going to be talking about decision trees. So what is a decision tree actually? Decision tree is a supervised machine learning algorithm, which is generally used for both classifying tasks and regression tasks. And how it works is that it will ask you a series of questions, and each of these answers leads to another decision, which is similar to like a flowchart. So this is just a small example that I've taken. So in this example, let me just zoom it up. Yeah. So in this example, we are just checking. The question is a person fit or not? Right. So here, first we look at the age. If the age is less than 30 and if he eats lots of pizzas, then it means that he is obviously very unfit. Or else he is not less than 30 and he exercises in the morning, it says he's fit. Right. So if you're less than 30 and you eat pizzas, it means you're unfit. If you don't eat pizzas, you're fit. So in this way, many questions are asked one by one, and based on these, you arrive at a prediction. And that is how decision trees work. So now there are three key metrics that help decision trees work effectively. So the first is Gini index. So This is called as Gini impurity index, which is a metric that tells us how mixed the classes are. And entropy from information theory measures the disorder. And lower values mean purer splits. And there is another metric called as information gain. Information gain basically tells us how much useful information we gain after splitting on a feature. So let's say we have different features like age, maybe we have gender, we also have, let's say, the locality of the person, weight, height, and now we want to predict if a person is fit or not. So the information gain feature helps us to choose that one feature which would give us best results, as in highest information gain. And the third, important concept in decision trees is pruning. So since decision trees work on a question based, recursive question based, framework, it is possible that sometimes it can overfit, especially on small data sets. So pruning means we just cut off parts of the tree that are not contributing to the accuracy to make the model simpler and more widely usable, right? So now let's try to go through a quick demo for decision trees. Here I've actually taken um, a small number of features. So the features are income, credit score, and loan amount for five different people, along with a target which says whether a person will default on the loan or not. So one means the person defaulted on the loan, and zero means the person did not default. So the model, what it actually does is it learns. So given someone's income, credit score, and the loan amount, what is the likelihood that they will default on the loan? So this is like a classic, binary classification problem, which is what decision trees do really well. So as you can see, I have done the splitting of the data set into train and test. And then I've tried to fit the, I've tried to train the model and I've predicted it with X underscore test, right? So anyways, these are all some metrics that you don't really have to go through now. But then the end value is this. And now, in the end value, we can see that the Gini is zero, which means that all the samples in the node belong to the same class. As in, 100% of them are either defaulters or non-defaulters. And Gini value of zero indicates that there is perfect purity. Samples equal to 4 tells us that 4 data points ended up at the node, and value equal to 1 is the predicted class. So since we're predicting lone default, where 1 is defaulted and 0 is no default, it means that the model, predicted default for the X underscore test data point. So that's all for this video about decision trees. Thank you for watching. Hello guys, welcome back to another video. Today we're going to be talking about ensemble methods. And the two most common ensemble methods are bagging and boosting, right? So they have very wide applications from fraud detection to stock prediction. And the main goal of, Ansible methods in machine learning is that it's able to combine the predictions of multiple individual models, which are, you can call, they're called as Bayes estimators. Some call them weak learners. So we combine the actual output of multiple of these weak learners to try to get to a prediction. So that is how this works. And one of the best advantages of this is that since there is a lot of diversity, so different models predict differently, right? So this actually helps us to reduce errors and im- on a general scale, it improves the performance. And to show you how this looks, basically we have two main you know subsets in ensemble methods, which is bagging and boosting, right? So in bagging, what we do is we actually try to train multiple independent models on different subsets of the data set. So we would randomly pick and not pick certain tables or certain rows and columns in a data set and then train the models individually to arrive at an answer. So this actually runs parallelly, right? So each of these independently arrive at a solution, and all of these solutions are combined to get the final output. That is how bagging works. Now moving on to boosting. And yeah, bagging, the full form is bootstrap aggregation. And in this, since each model gets a slightly different view of the data, the predictions are sort of averaged. And you take a vote in case of classification, as in, um, is the prediction one more or zero more? And for regression, you just take the average. So boosting is a method where you try to train the model sequentially. Each one sort of learns from the mistakes of the previous, right? So initially, in the first few iterations of boosting, the model focuses on the entire data set and tries to, get them right. But in the later ones, let's say in step number three, right? In step number three, there are three data points that are not predicted correctly. So misclassified, right? So step number four, the goal would be to sort of correctly predict these three data points. And how you would do that is like you would give them more preference. And what I mean by preference is like you sort of increase their weights or importance in such a way that the model knows that this is something that I actually need to get right. And at the end of the whole cycle, we can of course determine the height of the boosting algorithm even for bagging. So we have all of these parameters available, but at the end, all the weak models in boosting are combined into one strong learner. And some examples or variations of boosting are ADA boost, gradient boost, XG boost, and etc. So boosting, the main advantage is that it is able to reduce the bias and it makes the models more accurate. But the only risk is that the risk of overfitting if it's not tuned well. So the hyperparameters that you use in the boosting algorithm is something that you should carefully choose. And there are a lot of tools for choosing that as well. So we have the grid search CV and libraries like that to help us with it. So just to summarize between bagging and boosting, bagging is a parallel method which reduces variance and the data is randomly sampled And some one example of it is random forest, whereas boosting is a sequential method which reduces bias, and the data is chosen such that more weight is given to the data points that are incorrectly classified. And some examples are XGBoost and AdaBoost. Some examples of real world scenarios where this could be used is medical diagnosis, spam detection in the case of bagging, and in the case of boosting, image recognition, customer prediction, etc. Now let's look at an example. So this is the same data set as before, where we have a loan prediction system, and we are trying to predict whether the loan will be paid or not. Very similar approach. I've taken the data set, split the target and the features, done the train test split, and performed the random forest classifier, which is bagging and the boosting, right? And now I'm trying to, do do the testing, and let's look at the results. So yes, in bagging we can see that there is the accuracy is 1, so perfect accuracy. But whereas in boosting, it's just 0.66. So maybe if we tune the hyper parameters well, and maybe change up the eval metric and do stuff like this, even the boosting accuracy will increase. So that was a brief introduction about bagging and boosting. Thank you for watching.
Hello guys, welcome back to another video. Today we're going to be looking at another popular machine learning algorithm which is called as SVM. So support vector machines, or SVM, is a supervised learning algorithm which is used both for classification and regression tasks, but the main use case of this is in classification problems. So the key idea is to find the best possible boundary called as a hyperplane that sort of separates the classes with maximum margin, right? So you can see here that this is a unique line that is able to sort of split these two classes, and the goal has been to maximize this margin, right? There are some key terminologies involved in support vector mechanisms. The first one being the hyperplane, which is the decision boundary that splits the feature space into classes. And we have something called as the margin. So margin is the distance between the hyperplane and the closest points to it, which are called as the support vectors. And the goal of SVM is to try to maximize this distance or the margin. And the why do we maximize this margin? This is because at any given point we would like to minimize errors, right? And the more far away data points are from the best fit line, the less likely are errors, the frequency of errors. And for this reason, we try to increase the margin and maximize it. And then we have support vectors, which are the critical data points that are closest to the boundary. And these support vectors uh, are directly involved in sort of defining the optimal line. And if you make changes to any of these, the decision boundary would actually shift. So there is also two different types of SVM, support vector machines. One of them is linear and another is non-linear. So not all data can be separated by a straight line. And that is where a kernel comes in. So using the kernel trick, we can sort of transform data into higher dimensions where a linear separator is possible. And some common kernels that are used are the polynomial kernel and the RBF, which is the radial basis function kernel and the Gaussian kernel. And some of the popular use cases of SVM are in face detection, bioinformatics, fraud detection, credit credit risk detection. And since all of these are very much popular classification tasks, SVM is able to perform these with high accuracy and well-defined class boundaries, even with small and noisy data sets. Okay. Unlike the decision trees or logistic regression that we have seen till now, SVM will focus on maximizing the margin rather than just fitting the data. So that was a bit about SVM. And now let's try to look at an example. Just like the previous examples, I have taken a data set of a bunch of people with varied incomes, credit scores, and the amount of loan that they have taken, and the default rate. Not default rate, but like the default metric, right? And our goal here is to classify whether we will pay back the loan or the person won't pay back the loan. So of course, like any, so these are the data points. And here, of course, we just try to do a train test split, just like any other example. Yes. So here we just do a train test split on it. We also do a scaling of the data points. So what is the point of scaling data points? So here we can see that, different metrics like income, credit score, and loan amount have different scales. As in, we would ideally like all of them to be between, let's say, 0 and 1, or something in, something that is has a uniform range, so that um, you know, one of these metrics shouldn't be contributing too highly to the end result just because of how big the number is rather than the relative scaling. So here we perform the train test split and we train the SVM model on the training data. We choose the RBF kernel, which is a popular nonlinear SVM technique, and some other parameters that we will come back to. And we try to predict the test points. We can see that we have gotten a very wonderful accuracy of 1. So it just correctly classifies all the testing data points. So this was just an introduction to how SVM works. Thank you for watching.